Thank you. In the name of Allah, the most gracious, the most merciful, praise be to Allah, and peace and blessings be upon the messenger of Allah, our master Muhammad, and upon his family and companions altogether. Now to continue, O Allah, teach us what benefits us, and benefit us with what you have taught us, and increase us in knowledge. In the previous episodes, we discussed differential protection and the characteristic curves analysis specific to several global relay manufacturing companies, including Siemens, ABB, Micom, and Sir Relays. All differential protection relies on its operating method or its functioning on what is called low impedance-based differential protection. This means that there is also protection known as high impedance, unbiased differential protection. Of course, yes. So stay with us. For the national revival, the high impedance differential relay is used to protect several equipments in the electrical system, the most important of which are the generator, bus bar, motor, reactor, and auto transformers. It is not used with the normal transformer with separate winding. The high impedance restricted air fault can be used to protect each winding of the transformer separately and separately. What was meant is that it can be used for protection together due to the differences on the transformer terminals. It started being manufactured based on a law stating the sum of the currents entering a point must equal the sum of the currents leaving it. This type had a drawback in its early manufacturing, causing instability during natural current imbalance or external faults. Research sought solutions to stabilize the relay during external faults, switching transients or natural currents. These issues were solved by adding components in series, creating a midpoint, as explained earlier. It operates incorrectly, especially in cases of natural current imbalance or external faults. Research sought solutions to ensure the stability of the relay for external faults, switching transients, or even in cases of natural currents from motor starting or transformer energization. These problems were solved with one of two methods, either by adding components in series, becoming a midpoint referred to as differential relay or percentage differential relay, using the concept explained earlier. Either by adding in series, which then becomes a midpoint, and at that point it is referred to as either differential relay or percentage differential relay, which uses the concept we explained in detail earlier. Differential relay or percentage differential relay, which uses the concept. And this is what we explained in detail earlier. Or these problems can be solved by adding a high resistance in series with the operating coil, and then the name of this relay becomes, and it was named because of the addition in series with the relay. It is named this way, because of the addition in series with the relay. And this will definitely increase the burden load on the CT terminals. This modification introduced to the differential relay aims to ensure that it is not affected by CT saturation at the terminals of the protected element during external faults, allowing it to maintain its stability. So how is this achieved? Stay tuned for the national revival. In CT saturation during an external fault, the relay misidentifies an internal fault. A high resistance is added in series with the relay, diverting current through the saturated CT, stabilizing the relay. It will think internal fault, not external, causing a wrong trip. To fix this, a high resistance was added to the relay. Thus, more current flows through the saturated CT, which has lower resistance than the relay. Thus, the relay stays stable. See how current flows in a closed path during CT saturation, avoiding the relay. By passing through the relay's path with the high resistance, the relay is not affected by this problem and remains stable. Notice in this image how the current flows in a closed path at the moment of CT saturation without passing through the relay's path. Embassy de Français Protection. A special type of differential protection adapts to situations during current transformer saturation, maintaining the stability of the protection system. In this case, one of two things will happen. Either the CT does not saturate and the relay does not trip because currents sum to zero, or one of the CTs saturates, so the secondary CT acts like a short circuit, causing an imbalance. The unsaturated CT's fault current finds two paths, through the relay with high resistance and through the saturated CT. After adding high resistance, the fault current from the unsaturated CT finds two paths, through the high resistance relay or the saturated CT. Most current flows through the saturated CT due to its lower resistance, leaving insufficient current for the relay to operate, thus unaffected by external faults. For internal faults, the relay detects when fault current flows from both CTs in the same direction. If only one CT feeds the fault current, it still flows through the saturated CT, leaving little for the relay. However, internal fault current is higher, enabling relay operation. CT saturation during internal faults doesn't cause issues, as it indicates a current difference, prompting the relay to trip. For internal faults, the relay senses fault current from both or one CT. High internal fault current operates the relay. CT saturation in internal faults doesn't cause issues. Relay detects current difference and issues a trip signal. At that point, the fault current will be very high because the small portion of the current passing through the relay will be sufficient to operate it, as the internal fault current is expected to be higher compared to the same type of external fault. However, if one of the CTs saturates during the internal fault, it won't cause any problem because the occurrence of CT saturation means there is a difference between the incoming and outgoing currents, and the relay will issue a trip signal. Since the fault is internal, the trip signal will be normal and not erroneous. But does this mean that the issue of CT saturation during an external fault in the case of low impedance differential protection cannot be resolved? Of course, it can be solved. External fault, the case of course it can be solved. Scientists have developed solutions for these cases. High impedance differential protection is notable for its simple design, ease of handling, and stability over low impedance differential protection. Its widespread use is due to engineers' extensive experience. It has long protected electrical systems, with modern stations often using it for busbar protection. However, technical issues needing manufacturer intervention have led to challenges, prompting a return to traditional differential protection. This is because it has been used for a long time to protect electrical systems. At one point, modern stations began to use it exclusively, especially in protecting the bus bar, as it is the most advanced and modern. However, after encountering some technical issues that could only be resolved by the manufacturer, engineers faced challenges in dealing with this type of protection during maintenance, operation, or during faults. This made the management decide to revert to the traditional differential protection once again. The renaissance of a great nation. What is the difference between high impedance differential protection and low impedance differential protection? We will mention the main differences so you can distinguish between them. Typically, high impedance differential protection is activated by connecting all the secondary CTs in parallel and then connecting their output to the relay. Therefore, all the connected CTs must be accurate and have exactly the same specifications. CTs in parallel are Class X, British, or Class BX, European. Identical CTs in parallel are a drawback of high impedance protection. For low impedance protection, identical specs aren't needed, allowing different CT ratios or mismatched polarities. The requirement for CTs connected in parallel to be identical is a drawback of high impedance differential protection because it is impractical. Minor differences will always exist, even with CTs of the same specifications from the same manufacturer. Additionally, the CT core used for high impedance protection cannot be shared with other protections. Conversely, low impedance protection does not require CTs in parallel to have identical specifications, which is advantageous. Different CT ratios and mismatched polarities are permissible, allowing for easy CT ratio matching or adjusting CT priority within the relay without rewiring. Furthermore, the same CT core for low impedance differential protection can be shared with other protections, enabling its use for both differential and restricted earth fault protection. This allows for easy CT ratio matching or adjusting the CT priority within the relay without needing to rewire the connections. Also, the same CT core used for low impedance differential protection can be shared with other protections in the same relay. This means you can use the same CT core for differential protection and also for restricted earth fault protection. The main reason we can share the same CT core across multiple protections is that it has a low burden. This means that the CT burden won't be high, and since the higher the burden on the CT terminals, the greater the likelihood of the CT entering saturation. And uses himself bravely to protect the The CT core is shared across protections due to its low burden, reducing saturation risk. Low impedance protection has a low secondary burden. A stabilizing resistor ensures stability during CT saturation, allowing reduced relay settings. High impedance protection is more stable under disturbances. A metro cell protects the high impedance relay and circuits from high voltages during faults, as all CTs feed it with large current. Low impedance protection has a lower secondary burden than high impedance protection. A stabilizing resistor is added to the relay for stability, allowing reduced relay settings. High impedance protection is more stable against external disturbances. A metro cell, a nonlinear resistor, is used to protect the high impedance relay and circuits from high voltages during faults. All CTs feed high impedance with large current during faults, causing voltage rise at relay terminals, risking damage. Severe CT saturation may occur, making the CT behave as if its secondary is open. We may need a nonlinear resistor, metro cell, to protect the high impedance relay and circuits from high voltages during faults. All CTs feed the high impedance with large current, causing a significant voltage rise at relay terminals. Severe CT saturation may occur. This causes voltage to exceed rated values, risking CT damage without the metro cell. The metro cell protects the relay from voltage spikes. The voltage will rise significantly at the relay terminals, potentially damaging them. Severe saturation of the current transformers may occur, causing them to behave differently due to increased burden during faults. The voltage will exceed the rated value, and the flux inside the core will rise, causing issues for the CT if the metro cell is not used. The metro cell protects the relay from voltage spikes by changing its resistance with voltage. As voltage increases, its resistance decreases, directing current through it instead of the relay, thus protecting it during surges. The metro cell serves two main purposes: protecting the relay input by limiting secondary voltage during a fault and protecting the CT from high voltages. The resistance changes with voltage. As voltage increases, resistance decreases, directing current through it, instead of the relay during spikes. Normally, low voltage means high resistance, preventing current flow. The metro cell serves two purposes: protecting the relay by limiting secondary voltage during faults and safeguarding the CT from high terminal voltages. In the image, the disc-like object is the metro cell, connected parallel to the relay and resistor. The brown resistor, the stabilizing resistor, is in series with the relay. Its resistance was high and prevented current from passing through it. So we can say that there are two main purposes for using the metro cell. The first is to protect the relay input by limiting the secondary voltage to safe values during a fault, and the second is to protect the CT itself from high voltages at its terminals during a fault. The metro cell, connected to the relay and resistor, limits high voltage to safe levels. Engineers often think it protects the relay during an open circuit at CT terminals, which is true if placed there, not at relay terminals. How did a significant voltage rise occur at the relay terminals if the metro cell was not used? This high voltage could damage the relay and all the connected circuits. Also notice in this image that after using the metro cell protection, the high voltage values were limited to safe small values. There is a common mistake among many engineers. If you ask them what the function of the metro cell is in high impedance protection, they might say it protects the relay during an open circuit at the CT terminals. This answer is correct if the metro cell is placed at the CT terminals, not at the relay terminals, as shown in this image. This is primarily to protect the current transformer from dangerously high voltages at its secondary terminals, which can occur if one side of the CT is accidentally left open while a high current is flowing through the primary, especially during fault currents. This metro cell can be used at CT terminals to protect personnel and equipment, as the voltage at the secondary terminals of an open current transformer can reach or exceed saturation voltage, depending on the primary current. Typically, a metro cell is used at CT terminals for transmission line protection, where secondary voltage is highest, often exceeding 2000 V RMS. In contrast, 100 VCTs for busbar or transformer differential protection usually range from 500 to 800 V. This is due to the highest fault currents on transmission lines, which can reach up to 20 times the CT's rated current. Its value exceeds 2000 V RMS, while the 100 V for current transformers in busbar or transformer differential protection typically ranges from 500 to 800 V. Fault currents on transmission lines can reach 20 times the city-rated current. For high voltage busbar protection, the midpoint voltage of the CT is much lower. Busbar protection detects CT saturation during severe faults using low impedance differential protection, or a stabilizing resistor. The maximum expected fault current on the transformer can reach up to 6 times the city-rated current. However, for the current transformer used for high voltage busbar protection, even though the fault current on the busbar may be similar to that on transmission lines, the midpoint voltage of the CT used for busbar protection is much lower than that of the CT used in transmission lines. Busbar differential protection detects CT saturation during severe external faults. It trips instantly. The midpoint voltage increase aids protection devices, but is dangerous if the secondary opens accidentally. To prevent this, install a nonlinear resistor, metrocell, or carrier transformer protection unit when midpoint voltage exceeds 3500 volts peak or 2500 volts RMS. The increase in the midpoint voltage of the current transformer, while beneficial for protection devices to ensure that the current transformer can operate with the required accuracy during very high fault currents, can be very dangerous if the secondary is accidentally opened. During the passage of large holiday currents, and to avoid this problem, according to the standards followed by the American code IEE or the British code PS, a nonlinear resistance metrocell or a carrier transformer protection unit must be installed on the terminals of the current transformer when the value of the new point voltage exceeds 3500 volts peak or 2500 volts RMS. Pick up 2500 volts RMS. Avoid voltage rise risks. No resistor if voltage low. See standard. Metrocell at relay terminals limits voltage, protects CT. At CT terminals, protects CT if open with high current. For low impedance differential protection, no stabilizing resistor or metrocell needed. Phase differential characteristic ensures stability. If the metrocell is placed at the relay terminals, its purpose is to protect the relay input by limiting the secondary voltage to save values during a fault, in addition to protecting the CT from high voltages at its terminals during a fault. However, if the metrocell is placed at the CT terminals, its main purpose is to primarily protect the CT from high voltages at its terminals in case one of its sides is accidentally left open, while a high current is flowing through the primary side. If one side is open with high current, low impedance differential protection doesn't need a stabilizing resistor. CTs feed the relay winding without parallel connection. High impedance uses fixed current for relay operation. To achieve the required balance, there is also no need for a metrocell because each CT feeds into the relay winding independently and the CTs are not connected in parallel. Additionally, the flow of current in low impedance will not cause a voltage rise as it does in high impedance. Now, let's return to the differences between low impedance and high impedance differential protection. In high impedance differential protection, the differential current setting is defined by the current value at which the relay is intended to operate, represented as a fixed coupling or what is called fixed current, along with the voltage value to be applied to generate this current, and the value of the resistor connected in series with it. So it's also essential to know the wiring data to obtain its resistance values and use these values in calculating the voltage setting. Meanwhile, the differential current setting in low impedance differential protection is described by the minimum differential pickup current and the slope values 1 and 2, represented as a linearly increasing coupling in addition to the value of the unrestrained current. It is characterized by its low cost, simple design, and easy testing, unlike others, which have a high cost and a relatively complex design and testing process. It has the ability to store faults while nothing can be stored in the other. There is a push for protection in the high impedance. Some companies have used and then placed a high resistor in series with it to convert the protection, as shown in this image. In this case, we benefit from what is available in the recorder. Companies use a high resistor in series to convert protection. Recorder features help. Measurement accuracy in high impedance protection depends on secondary circuit resistance. Large CT cables minimize errors. In low impedance protection, secondary circuit resistance isn't a concern. High impedance lacks communication cables. Low impedance may need them. The recorder is located in. The accuracy of measurement in high impedance differential protection depends on the secondary circuit resistance, so it's better to use large CT cables to minimize these errors. In low impedance differential protection, the resistance of the secondary circuit is not a concern. High impedance differential protection lacks communication cable, while in low impedance, it may require a communication cable between the start and end of the line, the 87L, and between the bay unit and the central unit in the 87B. Any failure in this communication could lead to differential block limit. One of the main issues that low impedance differential protection may face is future expansions, as it requires a CT input for each breaker in the busbar protection. Communication failures between the bay and central units can lead to differential block limits. Future expansions pose a challenge for low impedance differential protection, requiring a CT input per breaker. Without a spare CT input, expansion means modifying CT circuits to connect in parallel. Consider expansions during design and configuration. If the station is expanded, I must modify CT circuits to connect in parallel on the same input. Future expansions must be considered in design and bus bar configuration. CTs in parallel must have the same ratio. CTs should connect only to load circuit, avoiding external sources feeding fault current to prevent relay errors. Ensure total load current from CTs does not exceed relay CT input or winding rating. If future expansions use high impedance differential protection, new CTs can be added to existing circuits in parallel. CTs in parallel must have the same ratio. CTs should connect only to load circuit, avoiding external sources feeding fault current to prevent relay errors. We ensure the total maximum load current from these CTs stays within the current rating that the relay CT input or the relay CT winding can continuously handle. However, if future expansions occur and the bus bar protection used is high impedance differential protection, you can add the new CT to the existing CT circuits. But in this case, redo the calculations for the metrocell and the stabilizing resistor. And if adding feeders affects the current metrocell or needs changing or replacing. Trip speed for high emittance differential protection can reach 1.5 cycles, while low emittance can be under 1 cycle. However, in this case, it is necessary to redo the calculations related to the metrocell and the stabilizing resistor, and whether adding several feeders will affect the current metrocell, or if it will require changing its values or replacing it entirely. As for the trip speed or retrieving time for high impedance differential protection, it can reach up to 1.5 cycles, while in low impedance differential protection, it can be less than 1 cycle. It can reach up to 1.5 cycles, while in low impedance differential protection, it can be less than 1 cycle. It is not recommended to use it in protection, which requires opening or closing, as circuits must identify the part that needs to be disconnected, whether it is during a fault or not. This system is used in some stations, and it has been used to switch between the CT circuits when transitioning from. No protection method is superior. Users must weigh pros and cons based on applications and CT relay location. However, we tend to use it in line protection because it is not reasonable to pull the CT wires from the remote end. Switching between CT circuits when moving from one protection method is not better than another. Users evaluate the pros and cons of each based on applications and CT relay location. Generally, we use it in line protection, as pulling CT wires from remote ends is impractical. They must be in a specific area. We use it in transformer protection, as it simplifies handling outputs, harmonics, zero sequence elimination, and vector group correction. Kilometers must stay in a specific geographical area. It is used in transformer protection to handle outputs from different points on the transformer. It is easier to deal with harmonics and zero sequence elimination and the vector group correction factor. It is used with protection of one side of the transformer, alone or with others. Notably, in some stations, it has been used with other systems, usable both ways per design. Harmonics, zero sequence elimination, and the vector group correction factor. It is usually used with the protection of one side of the transformer, either independently or in conjunction with other systems. It's worth noting that in some stations, it has been used with other systems, meaning you can use it either way, depending on the designer's philosophy. You can use this or for it, and this depends on the designer's philosophy. The cost is determined. As for the differential protection of the cactus, it can be used as both methods are used in stations. As for protection in generators, it can also be used or inspired by the Renaissance of the nation. Two methods are used in stations, but in generator protection, one can also use or. Let's address the new question. How can we test the metrocell resistor in stations? The metrocell is a non-linear resistance, unlike regular linear resistance that follows Ohm's law, where V equals I times R. As voltage increases, current increases linearly. However, the metrocell has high resistance normally, and as voltage increases, current increases non-linearly. When voltage reaches a certain point, the metrocell becomes a short circuit. We can test it using the CBC 100 by selecting the city excitation curve knee point to apply voltage and obtain the voltage-current relationship. Notice we connected two cables from the AC voltage source in the CBC to the metrocell, then started the city excitation curve knee point card. We can test it using the CBC 100. Select the city excitation curve knee point to apply voltage across the metro cell and get the voltage current relationship. We took cables from the AC voltage source and connected them to the metro cell. Then we went to the city excitation curve knee point card and started it. How do we test high impedance differential protection? The way to test this protection is by applying voltage, not injecting current, and then increasing the voltage value until you reach the voltage level that triggers the pickup signal. And we just started it. Another question. How do we test high impedance differential protection? The correct way to test this type of protection is by applying voltage, not injecting current, and then gradually increasing the voltage value until you reach the voltage level that triggers the pickup signal. At the same time, we measure the value of the current that the relay has issued to this pickup by using a caliper, meaning we record the value of the pickup voltage and the value of the pickup current in the report, and then we gradually reduce the value of the voltage to record the value of the drop-off voltage and the drop-off current, and then calculate the value of the rest ratio, which is equal to I drop-off over I pickup. In the end, we calculate by applying a voltage greater than the value. We perform these steps for each phase separately. And with that, we conclude today's lecture. Thank God, the Lord of the worlds. Stay tuned for the next episode, where we will explain electrical line protection in more detail. Wishing you happiness and see you soon.